Welcome back, everyone. We'll start now the second part of the mini course of Professor Fernando Sanchez.
Okay, thank you very much. I'm going to write 2 or 3 things in the blackboard to remember a little bit what I was doing yesterday. No, I'm not going to write anything. There are no charts. At the beginning, I have a linear system. I have a section in x1 equal to 0. And what I want to do is to analyze the left Poincaré map. Easy. First restriction, which is not a real restriction because as I want to study Poincaré maps, I need to add this condition because in any other case, the Poincaré map will not exist. So this one different from 0. But then it is easy to check that this can be transformed into this system. Less parameters. Okay, I have a box here, a complete box. This is for also 2 or 3 months. Thank you very much. Okay. When I do this, then the section is exactly the same. And I have here a tangency point. The behavior is like this of the flow. And I have also add a new condition, which is this one. This is, again, this is a condition, but it is not a restriction because our Poincaré map needs this system. If I do this, then there exists a inverse integrating factor like this one. Well, this will appear in the slide, but I'm going to write it. In any case, something like this. It is too long for me to remember. Marco, I don't want to do this, but I have to remove this. I'm sorry. Please forgive me. Yes. Right, okay. Then, with this inverse integrating factor, we can now see that this system divided by this function is a Hamiltonian system, and it can be obtained just with a simple change of variables. The system is like this one. And if this is an Hamiltonian, then this field is conservative, or it is conservative in every region where this inverse integrating factor does not appear.
This is the orthogonal.
Yes, but it is, this is the following point. Yes. But it is conservative, it's important for the integrals, and it is also orthogonal to the flow resistance, and this is what I did. Small superior I did yesterday, and it is necessary for the second part of the okay, this is the Hamiltonian system, this is the vector field. And orthogonal. And then I'm going to construct the integral characterization, the equation written in terms of a special. Yesterday I did this, but I don't have any problem to repeat to fix the ideas a little bit. The idea now is to integrate here on this flow this field G. And then there are three cases. I'm going a little bit fast because I did this yesterday. There are three cases. One case where the equilibrium of the system is not inside. So since and now we have these two flows, and since the field is conservative, then this integral is zero in the complete curve. As it is orthogonal to this curve, then this integral is zero. As a conclusion, the integral on this segment has to be zero, and this is the first expression of this integral equation. if the equilibrium is inside the region, then the integral on this curve is exactly the same as the integral in this curve. And, well, here in this curve it is 0 because it is orthogonal to the flow. And here we have that this integral is going to be the same that here. How to calculate this one? Well, you can take the curve you prefer and you integrate it. I told yesterday that if you take a cycle, which is the usual thing, then you have to fight a little bit against the integral, but you can. It's not very complicated. I put this exercise and told you that there is a change that allows to do it in a better way, in a trivial way. Conclusion, the integral here, this segment, is equal than this integral, which is by t, etc. Okay, expression very similar to the previous one. And the last case, well, here it is change that you have to do. Well, something that I have forgotten to tell you is that all the slides of the talk are now in the website of the meeting. So if you can read it, you don't have to take notes and just look at here. And well, this change allowed. Well, this is not a change. It is a curve. It is an ellipse around this point, and the integral is immediate. Okay, so it's part of the exercise. And then this is the third case, which is when the equilibrium of the system exists and it is in this line, of course in the origin. In this case, you have that this open integral has to be 0. Choose here as epsilon, and here again it is 0 because the field is orthogonal. Okay. Here the value of the integral is this one, which is, and now I'm going to write below, and the integral between y1 and y0 cannot be calculated because it is an improper integral and it is divergent. Because when we write the integral here, you have t equal to 0, you have just this, so it is 1 over dy. And in 0 you have a point where the curve goes to infinity and the integral is also infinity. But you can consider this t stands for what is called the principal value of Cauchy, which is a way to compute these integrals in a symmetric way. If you take here epsilon and minus epsilon, then both integrals go, one of them to plus infinity, the other one to less infinity, and then they cancel. When you take the limit, then you obtain a value, and this value will correspond to the value of this integral, which is this one. So we have three cases. Tell me.
This case corresponds to the value a equal to 0, I suppose.
A equal to 0, yes.
Then
This is equal to 0, yes. And then this disappears, and this is what you have. Okay, the equilibrium is located, in one of the slides I said that the equilibrium is located if it exists in some point, I don't remember exactly, minus a over t, minus or a t over t, something similar. So the equilibrium is at the origin when a is equal to 0. So I have three cases, just three cases. I have, well, this is the explanation of the Cauchy principal value. The definition, it is, as I told you, as a symmetric way to compute these improper intervals. This will be the first part of the method. You have 1.5 maps, and then you can write these 1.5 maps as some integral equalities. There are three cases depending on the value of t, and t is 0, 1, or 2, depending on the case we are considering, living inside, outside, or on the section, the Poincare section. For the right Poincare have math, the only thing you have to do is to change the sign of the expressions. And, well, our first intention when we began to do this was to remove cases in the analysis of this kind of system, and this is something that it is obtained from here. You say, yes, you have 3 cases, right? Yes, but you have to study cases depending on the spectrum. You have many more cases. So this is a first good idea. And also, the flight time has disappeared. I don't have flight time in any place. So if I want to use these equations as closing equations for a Poincare map, for example, or for a limit cycle or whatever, then the flight time is not going to be there. Of course, there are integral equations. They seem to be very difficult. Now I will tell you that it is not so complicated to manage. Well, in terms of the parameters, we have the principal value of this expression is equal to these 3 cases depending on A. This is exactly what you were saying. If A is equal to 0, we have the last value, and 0, the equilibrium is outside, and this one is the equilibrium is inside. Let me tell you that the principal value for an integral which is convergent or with this continuous, the function is continuous, then it is exactly the same value. So we can put there the principal value, it is valid for all the cases. Well, now, the second part. And I think that it is the most interesting part. If I have this interval, and I work with this integral, is this something that I can translate to a real Poincare map? Or perhaps I can have this integral and the Poincare map is not going to exist. But here I'm going to prove, or at least to give the principal ideas to prove that both schemes are exactly the same. So this is the proof of the equivalence. With the integral, I can say anything that you want about the Poincare. And well, this is a sort of summary. Yesterday, I thought that I was being able to stop here, and then this was to remember. This is something similar to what I have written there. So I go fast. From here, this is the resulting. As I said, we will see that this Poincare map can be obtained directly from this equation. And to know how to do it, we must analyze a little bit exactly this. What is this expression? So let me tell you several cases to know exactly what kind of integral we are managing. If you see, here we have minus y over this expression, which is the expression of the ingress integrated factor just in the segment in x equal to 0. Okay? If you look at here, this cannot be 0. Okay? This cannot be vanished. And if a is different to 0, you can see that for y equal to 0, this is going to be positive. So I'm going to work just in intervals where this expression is positive. Because if it changes the sign, then this denominator is 0, and then it hasn't any sense. For the case a equal to 0, we have the principal value that solves all that. And imagine that you have a function like this. This is positive, this is negative. So, for instance, in this case, in the case focus, then we have a function like this one. Something similar. And it is trivial to see that for each y0 that you take here, you have just one y1 here. So it is very easy to see that there is bijective correspondence between y0 and y1 here. And this function is y, this is y and this is square, goes to 0 in the infinity. It is also improper integral, so this goes to infinity, and to infinity. This means that you can take the value you want y0 and the value you want of y1. So it is defined in all this kind of focus with a positive and what is the definition. For instance, another example, a saddle. In a saddle, this is going to be positive until this straight line and this straight line, that are the invariant manifolds of the saddle. And this is the place where you can define the Poincare map, or this interval is defined. I don't want to talk about the Poincare map now, but this is going to be defined just in this interval. How is this function? Something like this. They have, again, an improper integral, and in this case, the point goes to infinity, it is divergent, so you can take the value that you want here, you will always have a value y1 here. So you have exactly the same bijective relationship between this point and this point. Another more case, this is a degenerating case, that to put b equal to 0. What kind of integral we have here? Well, here this vanish, so you have something like this, and in this part you have this integral, and then exactly the same. This goes to infinity. If it is divergent, here it is also divergent. So for each y z you have a y1, etc. etc. Well, in the case a equal to 0, I have put here a center. You don't have any limits in this definition, in this interval, and in the origin you have to use 3 of the principal value of Cauchy, and then you have, for each value, you have one value here, and the origin goes to the origin. And this is a little bit special, and I will talk a little bit more about this in 2 or 3 slides. If you have a focus like this, then this is going to be positive in all the straight line. This function is going to be defined for every value of y. But since in this case you have the equilibrium side on the right, the expression of the integral equation, you have this is equal to something, which is 0. And then this means that there will be a small region here where you will not have an image of the points that are here. And this is exactly this segment, the segment that corresponds to the point that goes to the tangency, because if you go up, then you always have a Poincare map, but if you go down, then you don't have this Poincare map because everything goes to the origin. And this is perfectly reflected in the expression. The interval definition of the integral. Well, we cannot vanish. This is something that I told you 2 minutes ago, except for a equal to 0 at the origin. For this case, we have the principal value. F must correspond to a Poincare map, so this means that you will have this behavior. Therefore, the interval must have positive and negative values. And this allows us to define an interval in the following way. Let me try to write something here. I'm going to erase all of this. The solid case, if you want to have positive and negative values, taking into account that this is the tangency, then the only possible region is this one in the space. That is, this segment would be the interval of definition of this interval. For instance, if you have a focus with equilibrium here, something like this, all the interval is going to be valid because v is different from 0 in all the points. So you can take the complete range. But if you have e equal to 0, you have two different situations. This one that is saddle, or this one which is focus or ascent. For instance, I will put something like this with the equilibrium here. Sorry, what is this? Everything is correct. If you have a focus, then the inverse integrated factor phi is going to be positive in all these regions, and also in this point. Well, in this point it will be 0, but it is surrounded by points where it is positive. But here, this is not the situation. It is 0. V is equal to 0 here in this point, and you will have, I don't know, but you will have positive, positive, negative, negative. You will have a region with positive and negative points over this section. So this case must be removed, this case must be included. But in the definition of the integral, this can be done in this way. So, well, we choose C to be the unique maximal connected complement of R2, where R2 minus the zero set of V that contains positive and negative points. If you do this, C is, for instance, in this case, it will be empty. It will be empty. You cannot have positive and negative values on the segment, in this case, and in just one connected component. Okay? So you are removing this case. And once you do this, you can define now the interval in this way. This will be the interior of C plus 0. This is the trick to add this case and to remove this case. If we do not consider A equal to 0, then it is very easy to define the region. You could say, okay, take the maximal component or the maximal interval on this section where the function that contains the origin. It will be exactly the same. But if you want to have this case also A equal to 0, then you must do a little bit more complicated the definition. But at the end, it also works. Well, in this case, now we have the integral and the interval. Well, this is exactly the comment that I have told you. Yes, sir. Okay, so now we have the integral, the interval of definition, and now it is interesting to see some properties of F that are going to be used in this last proof of the equivalence. For instance, it is obvious to see that for A different to 0, F is analytic in all these interval of definition. Let me write this. This is just to illustrate a little bit. This is the interval of the last interval of the definition. Okay? In the southern case, for instance. I is going to be just this segment. But in this case, in this study, for me, it is not important, although for the Poincaré map, it is very important to know if y0 is positive and y1 is negative. This is very important. For this study that I am going to do now, it is not important for me to distinguish between them. I'm going to talk about y0 and y1 independently of the place they will be here. One we have to be positive and the other one negative. But for this part of the study, it is not necessary. So this is the complete interval from here to here. I said this because, well, when we finish with this definition, this equivalence of the Poincaré map, then we will have to use, for several problems, we will use another interval of definition that will be just this one for y0. That is, in this moment, it will be important that y0 is positive and y1 is negative, and then we'll take just this interval, only this one. But now we are considering both zones together. Well, it is trivial to see that f is analytic in this segment because it doesn't vanish, it is continuous, so it's trivial. For e equal to 0, you have to keep in mind the principal value. Well, in this case, it is very easy to see that when this interval is immediate, the interval is given by this logarithm, so f is going to be analytic in all the regions except for these two straight lines, y0 and y1. Moreover, this is something to tell you that in this case, if you go in the plane, f is a function of two variables. If you take limits when y1 tends to the origin of 0 and y0 is different from 0, then you have this limit. This is infinite and with minus sign here. But if you do exactly the same, changing the roles of y0 and y1, you have positive. This means that you cannot define the function in the origin. You cannot have just one value. So you could take there any value for the function. Well, something about the level curves now. The important thing here is the analyticity of the solutions. This is an implicit equation. F this interval equal to 0 equal to whatever, this is an implicit equation. And you can have some solutions that will be functions of y1 in terms of y0 or of the opposite. We could restrict all the work, all this study, just to places where y0 is positive and y1 is negative. Y1 is negative, but if we do everything together, then it is easier to prove this kind of properties. For instance, the analyticity is going to be immediate for the limit cases. Right? The theorem seems a little bit strange to say that this equation, f equal to any value, not the three values, 0 and the other two, no, any value, will give also this curve, level curve will be the union of the graph of two functions. But two functions that can be functions of y0 in terms of y1 or the opposite, two functions. Now I'm going to tell you, to show you some examples to explain this better. You have to prove this, it is not difficult. And with the examples that I am going to show you, it's even easier to understand. But more important than this is that both functions are solutions of this differential equation. And this differential equation is very important. It is obtained directly if you take derivative in this interval. If you take derivative, you obtain exactly this expression. That it is exactly the same than this cubic system. It is a cubic system because I remember this is the inverse different factor. which is on the integral is just this quadratic expression, and then this is the system. This is a cubic system. This is very important for us because they will give us a lot of properties, and this is in all our papers. This is I think that the principal idea. Tomorrow I will show you an example of how this is going to be used in our study. For instance, the examples. For instance, when A is equal to 0, what are the level curves of F? Well, in this case, since it is very easy to integrate, this logarithm you have two functions, which are an exponential, constant exponential times z, a constant exponential times z. They are straight lines, something like this. This is trivial. These are also the solutions of the system for E equal to 0. This cubic system for E equal to 0. So everything can be removed. This is trivial, but these are the solutions. And well, of all these functions, of all these values of Q, the one that corresponds to Q equal to, I don't remember exactly, pi t over t times square. The value in the middle, the value for A equal to 0 in the middle, this will be the solution, the one that have not associated, the physics is associated to this integral. Okay? And these are the pairs that I was telling you. In this case, they can be obtained explicitly. If A is different from 0, I think that it is better not to read this. I go directly to these two values. I think that it is easy. For the value 0, the integral equal to 0, then you are always going to have in this figure, the integral is trivial that y1 equal to y0 is a solution, this is a continuous. This is one of the solutions, and this is straight line. Okay, and the other one for 0 is the one which you can see here. It can be proved that this curve is also analytic. Of course, you have here an intersection. But if you desingularize the expression, then you can see that it is analytic also, and this will be exactly the graph of the one-Gareth map, if it exists. I prove that it is equivalent. Okay? And okay. All the other curves that correspond to all the values of the integral, for instance, not 0, the other possible values, well, this will be curves like this. And if you look at these curves, for instance, imagine -1. This curve you can put y0 as a function of y1, and this one also. y0 as a function of y1, and not the opposite. And in these curves, it is exactly the opposite. You can put y1 in terms of y0. So this is the reason why I have not said anything about the variables when I was talking about the functions. And they are analytic solutions of a cubic system. The differential equation is trivial to see that they are analytic. Where you can have problems, you are looking for a one-Gareth map, then y0 will be positive, y1 will be negative. It will be in this quadrant, the fourth quadrant, and here in these lines exactly for y equal to 0, or here in the straight line y0 equal to 0, in this one, in these places, you can have a point where you can define y0 in terms of y1, but not the opposite. So you will have analyticity for a function, but the inverse will not be analytic. Okay? So the analyticity is very easy to be proved in this case. Here, this has something that corresponds to a saddle, and this is the reason why. Well, this is the complete plane. This is not the complete plane because you have in this drawing this interval y is finite. So this is y squared, and then all these curves satisfy exactly the same properties than them. The proof of the theorem is very technical. You can find it in the paper. I think that it is not nice to prove anything here. It's very technical, but it is not complicated, not very complicated, because the principal idea is that all these curves are solutions of a cubic system, like the previous one. Well, do you have any questions? Something? No? Please.
From all these cubes, what are the interesting ones? Just when Q is 0?
Well, you have, this is the integral, and you know that the integral can take three different values depending on the equilibrium, the position of the equilibrium. If A is equal to 0, or positive or negative. In the case where this is 0, then you have these two poles, but the only important one will be this one, because it is in the fourth quadrant. And it will correspond to the Poincare. But if this is 2 pi times t, etc., one of the other values, I don't know, have this one, or another one, that is one of these curves. Yes, we could have studied just the three cases, but if you study the 11 curves, you are doing a complete study, and it is easier than going case by case.
The idea is that the Poincare map is one of these cubes.
Yes, a piece of this curve. I'm sorry, a piece of this curve. The piece which is contained in this. Sorry, in the fourth quadrant. Okay, and tell me.
You say that you can put y1 in terms of y0, this curve,
Yes.
the value of the 2. You can put the y1 in terms of y0 or vice versa.
Sí.
And this means, in some sense, the sign of the trace does not move, because the Poincare, you can go from 1, 0 to 1, 1, 1 to 1, 0.
No, it is really important.
It's not important, because in fact, if you see the integral, you can see that you changing the sign of y, all the integral remains the same.
Exactly. Well, something more, if you look at here, I am just interested in this fourth quadrant. So here you can write all the functions as y1 in terms of y1 in terms of y0, or the opposite, all of them. The only problem is here, when you have these vertical or horizontal points, because and in these points, it is trivial to prove here that the curves are analytic, and these points correspond to I think, sorry. No. Yes, I have an impression here, but I prefer to write this here. Remember the case of the dimension. Focus like this, with an equilibrium in this side. Imagine this. Precisely this. Sorry, let me try to. Now this a little bit better. This is y0, y1. Okay, in this case, you in the third quadrant, this is not y0, sorry. So this is x and y. This is y0, y1. And this is the fourth quadrant. This curve, yes, have y0, y1 here. You will have something like this. This will be the beginning of your curve. So, sorry, it will be something like this, no? Corresponding to it. So this interval is exactly this distance from here, and this this point is exactly the point where you cannot write y0 in terms of y1 in terms of y0. It is better to do the opposite. You have something like this, and it is difficult to study the analyticity of a function like this. You have to make a local analysis, but in our case, since this is a solution of a system, it is trivial to see that this function will be analytic, but if you write y0 in terms of y1, the opposite will not be analytic. Okay? Well, here, now this is the differential equation that I have commented previously. Well, this is not new. In this work, there was also an objection of this equation for linear systems, but in a different context, because it was done just locally to analyze curves going from one point to another point. It's a different context. We have this equation, and that's not only this. It's an equation that is valid for all the interval definition. Okay? And well, how to obtain the curve looking at this differential equation? You have to add an initial condition. So in that case, like this one, the initial condition will be just y0 is going to be 0. This is one of the cases where a is equal to 0. Okay. In this case, the condition that you have to add is that y1, the y1 obtained for this point is 0. And in this case, you have that y1 in 0 must be this point, on the tangency point. The curve that goes to the tangency. Okay, this is the way to obtain exactly the level curve of the system, or in this case, to choose exactly the curve of the vector field that corresponds to the Poincare map. This is just to remember exactly what I have said. These are the three cases, and this will correspond to this curve, and this in this case will correspond to this case or this case. Okay. Now, to prove the equivalence, now we must see that our implicit integral equation corresponds to a real Poincare map. And then something that you have to do is to see that the flight time can be recovered from this integral. And how to do it? Well, this is a property. These properties of the inverse integrating factor. Directly from the inverse integrating factor. And you can use this because as this system is a linear system, then the divergence is directly the trace of the system. And then it is obvious as this from this part, and you yes, the exponential, you say the exponential, but the logarithm, and then you obtain something like this. This is a way to recover the flight time, because I remember that this is v in a point, this is v in a point of the same curve after a time t, and this is the interval between 0 and t. If you put t like the flight time, you obtain directly t from that. But this is not. This is a deductive way to obtain the flight time by in the case that t is different from 0. But it is perhaps not the best way to do it analytically for our analysis. for our study, for our group. Okay, so here, this will be for Poincare map the flight time. If you are able to compute these values, then you have the flight time. Let me tell you that there is another way to do it. And it comes from this definition, the definition of an interval. Remember the three cases depending on k, and then it's possible to prove from here that you have this expression, that the logarithm of v in 0.0y1 divided by the v in the 0.0 y0 is going to be this value from here. Okay, and how to time from here the flight time? If you look at here, this expression are the same. V is this, so the flight time is going to be this, which is inside of this brackets. Okay. This is one of the exercises, but this exercise is very easy to solve because it is solved in this slide. There are several cases. It is not difficult, but I have decided to write the solution because I think that it is interesting to see. So let me go case by case, and I want to prove this. This is now I'm going to write it sometimes more in the next slide. And then I'm going to consider different cases. This is the general case. The determinant and A different from 0. In this case, look at this integral. If we write here the derivative of this part from here, then you have a logarithm. And you obtain the logarithm we are looking for. And then this is what we do here. We write what we need to have a logarithm here and the rest of the expression. If you do this, you obtain directly the expression that you have before. Okay? Exactly, you have to move something this from here to here and to do some manipulation and you obtain it, which is exactly what I wrote in the first slide, in the previous slide. When D is equal to 0 and A is different from 0, I'm talking just about parameters, integral, especially I'm not talking about the Poincare map. Sometimes I have said something about the Poincare map in order to make it easier to understand what I'm doing. But remember, I'm now remind that I am trying to prove that from the integral expression I can obtain a Poincare map. So I'm just using parameters and the integral expression. In this case, this implies the case D equal to 0. D is equal to 0 and A different from 0. This implies that you have the integral equal to 0. And then in this case, D different from 0, but this is implied by D equal to 0. This solution directly. It will be the degenerated case. It is in the first case when you don't have any equilibrium, so this is why the integral must be 0. Okay, but in this case, for t different from 0, imagine this expression. You have removed d, you have this, just this expression, right? This is this integral. It is clear that if you multiply times t, you obtain the logarithm here. So you will have this expression automatically. And like t is equal to 0, you must remove this. This is just for t obviously positive. Okay? So this is immediate. For the case t equal to 0 is trivial. If t is equal to 0, this disappears, but you have the logarithm of this over this, but if t is equal to 0 and t is equal to 0, then you only have a squared. A squared here, logarithm of 1 is 0, so it's trivial. And the last case, when d is different from 0 and a equal to 0, this is the case where we have the equilibrium at the origin. In this case, this implies that d must be positive and e is 1 is the value, the three values, one in the middle. corresponding to E equal to 0. And it implies this because it must be a focus or a center. And then, well, here it is trivial that this is your integral. You can integrate this, you have this logarithm is this one, and this is exactly what you have to prove. Okay? This image. If you want to have everything in the slide, you have to see if I have done it correctly, then you can. If you find some mistake or something, please. Too many years working in this to find out a mistake in this place. And well, recovering the left quadrant, this is the last result. It is not, from my point of view, it is not very complicated. This is the usual thing when you finish the proof of a theorem, you say, it's not too complicated. But it has a lot of details. We must forget that we are working with quantitative math. You just have an equation and cases and parameters, and then you must prove that there exists quantitative math. What the theorem says is that if you have this condition it means that, well, you can have a quantitative map if the integral this integral is equal to one of these three values. In these cases, depending on the value of A, then y will be the left quantitative map y0, and moreover the flight time is this one. We have proved this values. This is the theorem. The proof is very complicated and very long. I want to tell you the ideas, principal ideas of the proof, and these are geometric ideas. Well, you see here some technical details about the time, some trivial cases. What we have to prove is that if phi is the flow of the system, then the flight time applied on this, the flow applied on this flight time, this expression, is going to be with the initial condition 0, y0 is exactly the point 0, y1 when this point corresponds to the point half mark. This is what we are finding. Yes, I think. So, okay, this is an equivalence that has been obtained previously with the flight time. On the other hand, we know that the logarithm of this, these are the two equivalents, the two expressions that I gave when we were talking about the flight time. So what you obtain here is that these 2 points, these points are in the same level 2 of the expression of V. That is, all of these points are at the same level 2 of this V. And how to use this graphically? Imagine that this is the point y0, and what we have obtained is that this is curve, and we stop here. That is, the flight time is not exactly the flight time. What I'm going to prove here is that this point is going to be here, and this is a point graph. Okay? And then, in this region, which is surrounded by this point, this curve, and here, this level curve of V, it is, I think that I stop here. Tomorrow I will begin with this because I know that there's 2 or 3 details that I have to tell you in a better way. So I stop here, and tomorrow I will finish this equivalence, and I will give you 2 examples how to use this to solve real problems. Okay? I stop here.
Let's thank Professor Fernando Hernandez. Time for one question or comments if there's anyone. have some comments or questions. That's it.
I look now. I was looking at the
Find the taxi.
the taxi wheel.
Trying to have the taxi driver at
For our next speaker, it's an honor to present Professor Colin Christopher from University of Plymouth. Professor Christopher will talk about Liouville integrability of higher dimensional systems.
Thank you very much. Very much like to thank the organisers for this very special meeting. And I want to talk something a little bit different from most of the topics today, which is going to be more on the algebraic side, but very much the inspiration for it comes from trying to understand dynamical systems and the topology of it and what's going on there. So this is joint work initially with Waleed Aziz, and then recently the team's changed more to Clara Plantesi and Sebastian Walcher. And the idea is as follows. Suppose we have a vector field, I'll write it in this form, and I'm interested in the case of 2D and 3D to begin with, and then I'll explain how it generalizes afterwards. So we've got a vector field like this, or maybe you prefer to put it in this form: x dot is p, y dot is q, and maybe z dot is r. And these are it's a polynomial equation, so p, q, possibly r are polynomials in x, y, and possibly z. And the idea is, when do we have a Liouvillean or a closed form first integral in closed form? In other words, we can give an explicit expression for this first integral such that when I add the vector field on this function phi, I get 0. In other words, phi is a first integral. So my first aim is to spend a little bit of time trying to explain what we mean by something that is expressible in closed form. So we want to spend some time thinking about this, and then to explain a little bit about Singer's theorem, which is a classical result in this area, which solves the problem in 2 dimensions, and then explain how we can extend that to 3 dimensions, and if there's time left, what happens in the general case in n dimensions. So the specific type of closed form that we're going to look at are called Liouvillean extensions. And the idea is very simple. We start with some base field, which for us is going to be c of x and y, and again possibly z, so rational functions in x and y, and then add terms like logarithms, exponentials, integrals, and solutions of algebraic equations. And we need to do this in a more precise way, so this is we're going to need to explain this a little bit using field theory. So I'm going to start with my base field, which I call K0, and then we're going to build a tower of extensions to finally get to my Liouvillean extension at the end. So this is a tower of fields, but we need to have some idea of differentiation, so that the tower of differential fields. And by that I mean that there is, in our case, there are some defined operators on these fields, so dx, dy, and dz, which are represented d by dx, d by dy, and d by dz. And we need some algebraic conditions, so first of all, that they commute. And secondly, that they obey some sort of Leibniz property, so dx of f times g is going to be dx of f times g plus f times dx g. And it turns out that if you work with this algebraic formulation, a lot of the things that we do in differential equations can be just looked at in a purely algebraic one without actually having to worry about the analysis at all. So we're picking out the algebraic part of dynamical systems, if you like. So we also need to say what these extensions look like, and there are 3 different types of extensions here. So I'm going to explain the middle one first, and then the other 2 will follow. So the first one is we just add a new element onto our field Ki, and we can assume that T is transcendental. So it doesn't obey any other algebraic equations. And then I need to say something about what T does. And so I'm going to use differential forms to try and make the expression a little bit easier. So dt, which is just shorthand for dt by dx, dx plus dt by dy, dy plus dt by dz, z. This thing is going to be equal to some delta. And I'm going to say that delta lies in Ki, but because this is a 1 form, I'm going to put a prime here. So when I write Ki prime, what I mean is Ki prime is the set of all things of the form, let's say a dx plus b dy plus c dz, where a, b, and c are all elements of Ki. And we're going to use this 1 form, 2 form notation to try and simplify some of the algebra a little bit and the expressions that we get. So as a consequence of that, this implies that the delta is equal to 0. And so we have a closed 1 form, and so analytically that means that the integral of delta is a well-defined function, but we don't have any analysis here. All we can do is say that this basically is represented by my algebraic element t. So this is an algebraic version, if you like, of saying that something is expressed by a closed 1 form in a lower field, and I add that on to move 1 step along my tower of extensions. The first condition is almost the same. But here I require that dt is equal to t times delta, where delta is in Ki prime. And again, this also implies that d delta is equal to 0. We're also going to assume that t is transcendental. And this one here corresponds to the analytic idea that we take the exponential of the integral of delta again. Because d delta is 0, it's a well-defined function, so therefore we can take the integral and then we can take the exponent of this. If in case you're wondering where the logs might be going here, we could take log of a, for example, would just be the integral of dA over a, and this would be my delta, and d delta would be 0 here as well. So we've got exponentials of integrals, we've got integrals themselves. Obviously, if I just took the integral of dA, I'd get e to the a, so I'd get exponentials here. And the final one is that Ki plus 1 is algebraic over Ki. And we'll always assume that we've adjusted things so that assume that Ki plus 1 is Galois over Ki. In other words, we add enough elements so that we can use a bit of Galois theory here if needed. Okay, so that's my expressions, and that allows us then to define sort of anything that we could write down explicitly. So, for example, x e to the y plus the logarithm of x plus y, and then maybe integrating that and so on. So there's a very large range of integrals here, and we want then to try and say, how do we characterize those vector fields which have those as integrals? So it's a very classical theorem in the sense of one that's very, very well known in the area of built with XIII problem dynamical systems. This is in 1992. Singer proved the following, that if phi is the abelian first integral of my vector field x, then there exists a function m which can be written in the following form. So it's a product of polynomials to various powers, they could be complex numbers, times some exponential term, and such functions occur a lot in this theory, so we give them a name and call them Darboux functions. Such that the divergence of x over m is equal to 0. I.e. that this is a Hamiltonian system and we can integrate it to give us ourselves a first integral. Let's just write that in a little bit of a different way. If we let omega equal p dy minus q dx, this is the one-form version of the differential equation x equals p, y equals q. So here, if we forget about the time element, solving this equation is the same as trying to solve the equation omega equals 0. And then the problem we're trying to find in the first integral is we are trying to show that d phi wedge omega is equal to 0. So that's exactly the same as asking that x of phi is equal to 0. And this condition here now becomes the condition that d omega over m is equal to 0. And finally, if I re-express this a little bit, I can write this as d omega is equal to dm over m, which with omega. So if we take this Darboux function here and then we calculate dm over m, we find that this thing is actually, let's call it alpha, is actually a rational one form. So it lies in, its coefficients lie in rational functions with dx, dy, and dz. And it's actually this form that Singer first proved the theorem, and then it's a small step to show that from this point you can integrate this back up and show that m must be a Darboux function over here. Okay. So this is very nice because these things are very, very standard when you're trying to find solutions to a Poincare center focus problem. These comprise a major, maybe one of the only two in real systems of different mechanisms for being able to show centers exist. And in fact, the Fi is equal 0 and the curve F equals 0 are invariant curves of the system, and so they have some sort of dynamical meaning as well. And the term here corresponds to limits of two curves coalescing together, and then this exponential terms appear. Okay, let's summarize what we've got, and let's see how we might go around proving Singer's theorem, and that will give us an idea about going into 3 dimensions. let's just assume that if phi is a Liouvillean first integral, and we're going to use the one form notation here because it's a little bit easier to work with. So if I is a Liouvillean first integral, then d phi wedge omega is equal to 0. And then because these are both one forms, this just tells me that d phi and omega are parallel. And so I could rewrite d phi is equal to omega over m for some m which is a Liouvillean function. And so that implies that d omega over m is equal to 0. So I should add that this m here is just Liouvillean. It's not the one that's over here, not the one that's the sinus theorem. It's not this specific one. It's one in some general extension. We want to show that it actually must be in this form. So if we re-express this as we did before, we get d omega is equal to dm over m wedge omega, and we can write this as alpha, where d alpha clearly must be equal to 0. So let's write out what we actually have here. So we have we want d omega is equal to alpha cross omega, and we have d alpha is equal to 0, where alpha lies in some Liouvillean extension. Let's call it k prime, where we have our Taran extensions. K is equal to k0 up to k n. So if I start with a Liouvillean first integral where phi is in my k, then I can do this reduction down here, and I can get this condition which I give a name. So, double dagger. And then the idea is the following. We could take this condition and try and show that at each step, if phi holds for some say for some alpha and omega, alpha in ki plus 1 prime, so one forms the coefficient of ki plus 1, then it also holds for some alpha in ki. And so the idea is that if we can prove this induction, we can work our way down until we get down to the base case, which is just the rational functions. So in other words, we have rational functions which satisfy this condition, which is exactly the place we are over here. We can turn my alpha into dm over m, where m is a Darboux function, and then we have sinus theorem. And it turns out that if you work with this setup, the proof is actually very, very simple. So I'm not going to go through the details in much detail because we'll do something similar in a moment. But just to give some idea of how we would deal with this. So in the first case, so this is the case where k of I plus 1 is equal to k of I of t, where dt is t times delta, where delta is in k plus 1 prime. What will we do? Well, an easy way to look at this case is to write the alpha that I've got as a power series in t. So I'm going to write it as a Lorentz series in powers of 1 minus t. And so it's going to look like the following. So it's going to be a highest order term, say alpha r times t to the r. That's alpha r minus 1, t to the r minus 1, and so on. And each of these alpha i's are going to lie, they're going to be one forms in ki, not ki plus 1, because we don't have any t in those. So we can always embed these rational functions in some series like this. Okay, then the idea is as follows. We plug this back into my equation here, and then by equating powers of t, I find a simpler solution which just involves one of these alpha r's instead of the ones that are up here, and I can actually reduce the system to an easy system. I'll give you more details when we generalise this in a moment, rather than repeating the same arguments again. I'll just say that we can do this quite straightforwardly. And the second case is quite similar. And in the third case, it's possible just to take, because omega doesn't change, omega is the fixed system, we can just take traces of this thing here. So we let alpha tilde equal 1 over n, where n is the order of the Galois group of Ko plus 1 over Ki, times the sum of the alphas sigma. And because this whole thing is linear in alpha, this just gives me that, first of all, that d omega is equal to alpha to tilde, wedge omega, and d alpha tilde. D commutes with the elements of the Galois group, so d alpha tilde is equal to 0. So again, I can descend from the bigger space to the smaller space, because by averaging over the Galois group, this now lies in the smaller space. Okay. If you work through the details of this, you can have a proof of sinus theorem in a slide or two. It's very straightforward to work through there. The key to doing that is to have a simple expression which you can integrate through. And so when we want to try and generalise that to 3 dimensions, what we want to try and do is to find say not the right expression, but what's a very helpful expression here that will allow us to do the same thing in 3 dimensions as we have in 2. So let's see what we can do in that result. So I'm going to work in the language of forms again, so we need to have some way of describing a 3-dimensional vector field using forms, and so we need to have 2 forms here. So I'm going to represent my 3-dimensional vector field as p dy dz plus q dz dx plus r dx dy. And then we need to just spend a little bit of time thinking about what that will mean in terms of our familiar quantities. So, for example, phi wedge capital omega equals 0 is exactly the same as requiring that x of phi is 0. And the divergence of x phi, so omega over m equals 0 is exactly the same as asking that the divergence of capital X over m is 0. This m is no longer an inverse integrating factor, it's actually an inverse Jacobi multiplier. And that has very similar properties, so in particular I'll come back to this a little bit later, but if we imagine we have some level curves of the surface given by a first integral, so let's say phi equals constant gives me some level curves from my 3-dimensional system, then in that system there are going to be some dynamics which is occurring on these sheets. And on each sheet, m is an inverse integrating factor. So what it means is that on any particular sheet, I can use this inverse integrating factor for starting from there and then integrating this up to get the first integral. And then what I need to do is I need to take some transversal through all the sheets and starting at some point here, then integrating around and getting some universal first integral from that. Unfortunately, doing that means that I get some strange dependence on C, and it may not actually fit into the algebraic situation very well. And we'll come back to that a little bit later on. Okay, so let's try and re-express the condition of having a Liouvillean first integral in terms of something simpler. So my first condition is that d phi wedge omega is equal to 0, where phi is in some Liouvillean extension, let's call it k. And so I could just rewrite that as omega wedge phi is equal to 0. For omega in k prime, with the condition that d omega is equal to 0. And conversely, if I know this condition here, and d omega is equal to 0, then with one integration I can move back up to this one. So although it wouldn't, going back from here to here, I might need to have add an extra extension, or an extra step onto my Liouvillean extension. Certainly, if there's a Liouvillean solution to this one, there's a Liouvillean solution to the one above by just taking phi is equal to the integral of omega. And in the same way, I could write this as omega over e to the integral of alpha, wedge omega is equal to 0, where here I've got e to the, where here my condition is that d omega over e to the integral of alpha is equal to 0. So in order to go from here to here, I just put alpha equals 0. But I've written in this way because of from Singer's theorem, we're getting some inspiration from Singer's theorem that this actually might be what we need to be considering rather than this one, because this is the typical thing that appears when we're doing Liouvillean situation for 2 dimensions. And again, this thing over this side will say that I need d alpha equals 0, so that this integral is well defined. And moving from here back up to here, this again is just one extension. I just take omega tilde is equal to omega over alpha. So this one is straightforward, and then the final step is just to re-express this in the following way, that I get omega wedge capital omega is equal to 0, and this condition that the d is equal to 0 just gives me that d omega is equal to alpha wedge omega, and I also have the condition that d alpha is equal to 0. And over here, moving from this condition here, back up to this one, is one extra step in the Liouvillean extension. Okay, so we've got a way of rewriting my equations in a form that looks similar to the one above here, but might be more appropriate in 3 dimensions. And that's indeed turns out to be the case. But things are a little bit more complicated here, and the step that causes the most problem is in fact the easiest step in Singer's theorem. So the easiest step for us was just taking traces. But if we try to take traces for this condition, we have a problem, because not only in this equation here, not only will alpha change when we add the Galois group, but also omega over here will change as well. So this is no longer linear, and so just taking traces itself won't really work. And in fact, if we take an omega and then we act on it by an element of the Galois group, we might in fact find that it's no longer parallel. In fact, these two things provide two separate solutions. So we need to work a little bit more carefully in trying to define how we're going to use the induction. So the idea is as follows, and again I think this goes back to maybe the papers of Prell and Singer, that rather than working with the extensions we've seen over here, we work with a slightly different tower of extensions. So we again start with Kn, and we produce a tower of extensions. This one, 0, which is 1. Okay? But this time we group all the algebraic extensions together, and we consider the following possibilities. First of all, that Ki plus 1 is an algebraic extension of Ki t, and again with the same condition that dt is equal to t times delta. 2 Ki is an algebraic extension of Ki t, and dt is equal to delta. And that happens for each of those extensions. So this is always for I greater than equal to 1. So all of these extensions are exactly one transcendental extension plus an algebraic extension. And that leaves the possibility that this last extension here is just an algebraic extension on its own. And that just takes me one step away from my base field, which was just rational. So the idea is that we want to work by induction, in other words, show that if this holds with omega and alpha in some element here, then we can then move down to the next element. So we can work our way from Ki plus 1 to Ki in each of these steps. And then we'll be just left with the final problem, working out what happens to just a pure algebraic extension of the base field. Okay, so let's try and write my omega and my alpha as series in T, but we have a small problem because this is an algebraic extension of T now, and so it's no longer going to be possible to write it as a simple power series. But we can write them as Puiseux series in the following way. So we could have, say, omega to the r, T to the r, plus lower order terms, where this is a Puiseux series, so it's in fractional powers of t, and so when it's fractional powers, they're fractional powers where the denominator is bounded by some certain size. So the denominator doesn't just keep on growing, it has some fixed size, but there's going to be some n of which the denominator will not be any bigger than n. And we can also write alpha as alpha s, t to the s, plus lower order terms. And now we want to apply the same logic that we did before, and so I'm actually going to give you the details this time how we're going to do that. So I'm going to take you through case 1, and case 2 is going to be more or less the same. So if we look down at this condition here, our star condition, so first of all, omega cross capital Omega equals 0 is going to mean that each of the omega k's also has that property. And when we look at this condition down here, also look at this one as well, so d alpha is equal to 0 is going to tell us that d alpha k plus k times delta wedge alpha k is equal to 0. Okay. So that's picking out two of the conditions here. There's one other condition that we want to understand as well, and it's this final one here. And here we're just going to look at the highest order terms in t of this, this equation here. Okay, so let's just split this up into two possibilities. First of all, when s is bigger than 0, in other words, there's some terms with positive powers of t, then we get an equation that alpha s wedge omega r is equal to 0. But we already know that omega r is going to be wedge capital omega is equal to 0, and so this implies that alpha s itself must be have the property that wedged with capital omega gives me 0. And we also know that d alpha s by my equation down here is just going to be minus k times delta wedge with alpha s. And so if we take omega tilde equal to alpha s, and we take alpha tilde equal to minus k times delta, then we can find that in fact it obeys exactly this condition down here, but now instead of these things being in ki plus 1 prime, they're actually in ki. So it obeys the start condition with omega tilde in ki prime and alpha tilde in ki. So that immediately takes me down the induction step in case 1. Just say, without giving the details, that case 2 is similar. So that just leaves us with the last case, which is case 3, which is a little bit more tricky. So I'm just going to describe, without actually proving the results, of what happens in this case. So in case 3, so we have a Galois group of k1 over k0, so that's the last step of the extension. And in fact, k0 is just my k, my base field. And I look for G0 is going to be the set of all sigma in G such that when I act this on, it remains the same. In other words, it has no effect on my omega. And then we consider n, which is going to be the index of G0. Okay. So there are two possibilities here. So the first possibility is that n is equal to 2. And so in this case, we know that G is a normal subgroup of the capital G, and so we can average over G0. In some sense. And that means that we've reduced to the case where K1 is just the base field with some square root added. And so therefore we get alpha and omega are just rational functions, well, they're rational one forms, but with coefficients in k with a square root of a function. And so the question then is, can we actually reduce any further? And it turns out there are examples, there exist examples where this cannot be reduced further. In other words, neither alpha nor omega can be reduced to the base case. So I'm not sure there's anything else you can say about these other. They're not very generic examples, but they do exist. Proving that they really work is quite complicated as well. Okay, so that's the first case. The second case is when n is bigger than 2. And in this case, we can choose alpha to actually lie in the base field, but not omega. And in fact, for interesting cases, we're going to actually have at least 2 independent 1 forms here. So omega 1 and omega 2. Let's say omega 1 is my original omega, and omega 2 is some image of it. So that when I act on with signal, what I get is some matrix times omega 1, omega 2. So here, just to make it explicit, the omega 1 is equal to alpha wedge omega 1, and the omega 2 is equal to alpha wedge omega 2. And it turns out in this case that A can be chosen to lie SL2C. So it has a very nice matrix form with complex coefficients. So over here we have it's a finite algebraic extension, and so this is a finite subgroup of SL2 of C, and so we know what those look like. They're either cyclic groups, they're dihedral groups, but we have to be a little bit careful here because in all these cases it's dihedral. Let me write it out first. There's A4 and S4 and A5. These are the familiar Platonic solid groups when we're working with in the projective projective sphere, in the Riemann sphere. But if we're actually working in SL2 itself, we've got to be a little bit careful because we don't get exactly the Platonic solids, we get a double covering of them. So we call these things DN SL2, A4 SL2, S4 SL2, and A5 SL2. So these are, if you like, twice the size of the normal groups that you get for the symmetries of Platonic solids. The cyclic group we can prove reduces to a Z2 action. And these 4 cases here, we can actually prove there exist examples where this actually happens. And maybe just briefly to say what those examples look like. So here my omega is going to be dy times f of x plus z times f prime of x plus f of x dx. So this clearly can be integrated. I just remove the d here, I integrate this thing, and the f of x's come from the Schwartz list of algebraic solutions of the hypergeometric equations. So by taking the f's as these standard, these very classical solutions, algebraic solutions of the hypergeometric equation, you can show that in fact the integral is not algebraic, and therefore it can't be simplified any further, and you actually get a system that works here. In fact, in this case, because d omega is equal to 0, alpha is equal to 0, but with a little bit more work, you can put an exponential term in here and prove that there actually exists examples of alpha not equal to 0, which can't be reduced either to alpha equals 0 or to the case where omega is in the base field. So these things actually work together. I've got 2 minutes to explain what happens in this. So that's the condition we have, and we haven't. We can give examples, but this is the best we can do in this case. What about in the general case, for general n? Well, we can say, again, we can take our one form. So this will be now an n minus 1 form, so it would be something like the sum of pi times dx1 wedge dx2, missing out dxi, dxn. And we then proceed exactly as we've done before. It really isn't much different from what we've done in cases 1, in cases 2, it's almost identical. But in case 3, we have a little bit more of a problem. So in case 3, we have alpha has a number of images. So alpha acting on sigma, where sigma is in my Galois group. The values, let's say alpha 1, alpha 2, up to alpha r. And then for each of these alphas, we get a number of omegas. So omega 1, 1, up to omega m1. And over here we get omega 2, 1, 1, 2, up to omega m2, and so on. And so we've got R blocks of m. And here we need R times m is equal to n. And then we get to very similar situations to the one over here. So we have m times r times n, or n plus n of these omegas, and we get a big matrix A. And this big matrix looks like the following. So it has a block structure. So at the big, zooming out, this little bit here is just a permutation of the elements SR. It's just there are R blocks here, and each block is m by m. Okay, so just looking at the blocks, they just look like permutations, and they're in fact just the permutations of these alphas under the Galois group. And each of the blocks actually lie in SL M of C. So there are little SL M blocks here, and they permutate the things around it. And then it's easy to show that in the case when n equals 2, then, which is the case we have, because we can't have more than 2 first integrals to a three-dimensional system, that either the blocks all have size 1, in which case we just have Z2, or there's just one big block, in which case it's SL2C, and that gives the classification we have.
We have time for questions or comments. So let's start. Thank you, Professor. We can now proceed for our poster section. We are back here at 15 past.
So let's start the last section. The next speaker is Paulo Viana. You talk about what on the computer.
Well, I would like to start by thanking the organizing for the opportunity to be here. For me, it's an honor to be in this stage presenting my work. So today I will present one of my works with Professor Armando Gazul, in which we try to approach in some way the Hilbert 16 problem. The communication will be based on this paper. It is available on archive and accepted for publication already. Well, I will assume that everyone here knows Hilbert 16 problem about upper bound for the number of limit cycles of planar polynomial vector fields. And let's see that XIII denote this upper bound. Of course, everyone here already know, despite the recent efforts to solve the problem, it is still open, I think, and it's very difficult. And in this communication, we try to approach this in a different manner. We did not try to solve it. We try to, in some way, characterize the vector fields that realize this upper boundary. So imagine for example, that the Hilbert number is finite, and we take a vector field that realizes this upper boundary. What do you know about this vector field? About this concrete vector field that realizes Hilbert number? You know nothing. You know, of course, you know that by definition that it has this number of limit cycles. But how many singularities does this vector field have? Does it have saddle connections? You know nothing about this vector field. In this communication, we try to approach, we try to provide some characterization of this vector field. And we did provide these two characterizations. The Hilbert number is an increasing function, and it is reached by structurally stable vector fields. So let's start by the part in which the Hilbert number is increasing. We know the famous lower bound of Professor Christopher and Lloyd, that the Hilbert number increases at least as fast as this order over here, m squared times log the m. But to have a lower bound given by a strictly increasing function does not imply that the Hilbert number itself is strictly increasing. Our first main result is this fact. The Hilbert number is a strictly increasing function. In particular, since we are not solving Hilbert number, this number here could be infinite. If this number is infinite, then infinity plus 1 is also infinite. And then we in particular prove that if for some degree the Hilbert number is infinite, then for every degree higher than that one, it will be still infinite. Of course, this kind of relation is not the first known relation about the Hilbert number. Professor Christopher and Lloyd also provide this relation, so we already know that the Hilbert number was increasing in some way. And in particularly, Professor Gazul and I were stuck with this property for a long time, and it take a long time for us to increase from this property to this one over here. That is, to drop the n plus 2 here to the n plus 1. So, regularly speaking, how did we prove that strictly increasing function? We take a vector field, realize the Hilbert number, and we embed it in the space of we take a vector field of degree n, realizing the Hilbert number, and we embed this of degree n, and we embed this vector field in the space of vector fields of degree n plus 1 in such a way that we use the Andronov-Hopf bifurcation to bifurcate one more limit cycle while the other ones persist through this bifurcation. And this persistence follows from our second main result, which is that the Hilbert number is reached by structurally stable vector fields. Globally speaking, I recall that a structurally stable vector field is a vector field that you can shake it in some way, and its topological characterization will persist, will endure this shaking. Of course, the hallmark work in this field is the characterization theorem from Professor Peixoto, but I recall that Professor Peixoto worked on C1 vector fields on closed manifolds. In the case of polynomial vector fields of a given degree n endowed with the coefficient topology, we have two main characterizations of structural stability. One due to Professor Sotomayor and one to Professor Douglas Schaffer. These characterizations are a little different since Professor Soto, for example, works with the Poincare compactification, while Professor Schaffer does not use this compactification. But essentially, the main characterizations of Professor Peixoto holds. So by structurally stable, you can imagine a vector field with at most a finite number of periodic orbits, all of them hyperbolic, at most a finite number of singularities, all of them hyperbolic, and without saddle connection. So you can think about this type of vector field. Let P of x denote the number of limit cycles of a given vector field, and let this sigma over here denote the set of structurally stable vector fields of polynomial structurally stable vector fields of degree n. Our second main result, that I mean from this phrase over here, is this one. What I mean by this result? If the Hilbert number is finite, then there is a structurally stable vector field realizing the Hilbert number. And if the Hilbert number is infinite, then there is a sequence of structurally stable vector field with as many limit cycles as you want. That is, you approach infinity by below. You have a sequence in which every vector field has a finite amount of limit cycle, but this amount goes to infinity. So from this result, we now have some characterization. Given a vector field that realizes the Hilbert number, we now know that we can choose this vector field to be structurally stable. And now I provide, in a few words, the key argumentation from all this communication. So take you take a planar polynomial vector field of degree n, realizing the Hilbert number. Suppose for now that the Hilbert number is finite. So someone realized this upper bound by definition. I take this someone. I multiply it by a rotation matrix. Cosine alpha minus sinus alpha, sinus alpha, cosinus alpha times the vector field. That is, you have a planar vector field. We are given a alpha, non-zero, we are rotating the entire vector field simultaneously. That product is this thing over here. This is a one-parameter family of rotated vector fields. With this family, we look at the famous work of Duff, in which he studies the family of rotated vector fields. And using Duff's results and Andronov results, we know this thing over here. That is, you have a vector field and you rotate it. Alpha is small, but can be positive or negative. What is this rotation doing with our limit cycles? if the limit cycle has odd multiplicity, it will endure this perturbation and will become hyperbolic. And if it has even multiplicity, it will either bifurcate into hyperbolic limit cycles or vanish. Intuitively, what is happening here? If you have a limit cycle of odd multiplicity, for example, then its first return map is something like that. The graph of the first return map. The rotation of the vector field, take this graph over here and moves it a little bit upwards or downwards, depending on which direction you are rotating the vector field. So if you look at this graph over here, of an odd function, of an odd limit cycle, if you go upwards or downwards, you will still have a zero of this first return map, and this zero will become simple. Will become, for example, this zero over here. So your limit cycle will persist and become hyperbolic. Similarly, if you have a limit cycle of even multiplicity, then the graph of the first return map is something like that. And if you move the graph upwards, the limit cycle will vanish. And if you move it downwards, it will bifurcate into hyperbolic limit cycles. So, and this, the beautiful part is that the rotation is doing this on all the limit cycles at the same time. You do not know where are these limit cycles, and you do not know how many limit cycles you have. But this reasoning is being applied on all the limit cycles. And essentially, if you look at this again, this is a machinery that either, given a limit cycle, it will either vanish or become hyperbolic. So if you rotate either way, the final result will be a bunch of hyperbolic limit cycles. Someone will vanish, but the ones that will remain will become hyperbolic. Knowing this, what do we do? We have a vector field. It has limit cycles. Some of them had odd multiplicity. This one will become hyperbolic for either direction of the alpha. And those of even multiplicity, some of them will bifurcate into hyperbolic limit cycles in one direction of the alpha, for example, positive alpha. And this one will bifurcate into for alpha positive and vanish for alpha negative. And the other ones of even multiplicity will do the opposite, will vanish for alpha positive and become true for alpha negative. Well, these are two integer numbers. Someone here is greater than or equal to the other one. If you suppose this without laws of generality, for example, you then rotate your vector field in the positive direction of alpha. You take alpha small enough and positive, and the limit cycles that will bifurcate into will compensate the one that will vanish. And at the end, you have at least the same amount of limit cycles, but now all of them are hyperbolic. In particular, the Hilbert number is realizable by hyperbolic limit cycles. Of course, the configuration of the limit cycles is changing, because some are changing and some are bifurcation, but the total number will persist. And the other properties of structural stability will follow from the density of the structurally stable vector fields inside the family of polynomial vector fields. Thank you.
Questions, comments?
Can you put the last transparency before this? Thank you. If n plus is strictly larger than n minus, the number of limit cycles increases. In contradiction that you have started with the maximum number of limit cycles, what happens in this case?
If the Hilbert number is positive, this implies that m plus and m minus must be equal. Indeed, if we start with a vector field realizing the upper bound, and it is finite, then by definition of upper bound, these two numbers must be equal. This is what we conclude.
Okay, I don't see, but okay.
I didn't really understand what you wanted to do. In a certain sense, you find the structural stability, but let's say you find that you realize the maximum number by structurally stable systems. This was known, this result. But you started by saying that you were going to prove that Hn plus 1 is at least Hn plus 1. Where do you do that?
Yes, it's a little more technical, and that's why I did not put it in here, but the main idea is, first we prove this theorem. Having this theorem, suppose, for example, that we are in the case of a finite Hilbert number. So we have a strictly stable vector field realizing that upper boundary. Since it's finite, there is a compact in the plane containing all those limit cycles. This is the compact over here. So everyone is here. We prove by a technical lemma that outside this compact, so this is the plane, there is a regular point, P, such that if you take the straight line passing through this point and having the vector of the vector field as directional vector, so you take this straight line over here, this straight line does not intersect this closed ball. So we prove this first for a technical lemma. Then this is L, this is a straight line L. You have the vector field P Q, realizing of degree n, realizing Hilbert's number, and the limit cycles are over here. And you have this point. We now multiply this vector field by this straight line. This is what I said by embedding the vector field on the space of higher degree. So we take this vector field over here. Suppose that this straight line is given by this equation over here. This is a line equation. You multiply this vector field by this line equation. So you have L. You have this vector field over here. This vector field has degree n plus 1, has this line as line of singularities, and since the line does not intersect the ball, the limit cycles over here persist. We now perturbate these straight lines. If I'm not mistaken, something like that. We put epsilon over here, and on the A over here we put a delta over here. And you have this line of singularities. We are doing something like that. We are moving. This straight line is a nucline because of this and this. So imagine as two different nuclines, and we are moving these nuclines by moving these straight lines. We do this in such a way that this point persists as a singularity, but now will be an isolated singularity, and will be, if you choose epsilon and delta with the right signs, will be a non-hyperbolic focus. And now you force a hot bifurcation here. And since the limit cycles inside here are hyperbolic, it will persist under these small perturbations that we are doing over here. So at the end, you have a vector field of degree n plus 1 having Hn plus 1 limit cycle at least.
Okay, I do not yet see it completely, but I understand the idea, and I believe in it.
So we have time for more questions. So let's thank the speaker again. So the next speaker is Lorenzo from Nicampi. From Nicampi, no, from Turkey. So,
thank you. First, thank you to the organizing for having me here, especially because we will talk to something that is not the usual topic of this conference. Marco, happy birthday. I guess I try to remember when I met you by the first time. I guess that we met in Dijon many years ago. But well, time goes. I think that many people say many things about, many positive things about Marco. And well, everybody says that he is a very generous person. And I always feel that. Thank you, Marco. And also thank the organizers. They are very creative. It's the first time in my conference that we have some pop slides during the coffee break. That is a great contribution. And let me now go to math. Well, I promise, as I told you, you are not working on this kind of topic. I am trying to explain the problem. Well, let me start with some motivation. But for me, all that I am planning to tell you is a joint work with my God, Gian from the Fluminense University in Brazil and in Huazan from Beihang in Beijing. We hope to have the pre-printed archive next week. Well, the motivation comes from all conjecture by Pallis. I think that is a conjecture that he stated in the 90s, sorry, that is a dichotomy. You have, for a dynamical system, you have two possibilities. Either the system is hyperbolic, or the second possibility is the system has a cycle. And for Jacob, the cycle, you have two possibilities. If you are in dimension 2, you have something that is called homogeneous tendency, you have a saddle. You consider the invariant manifolds of the saddle, and then you have some non-travel intersection, that is a homogeneous tendency. And if you go to dimension bigger than 3, the thing is that, well, in dimension 2, when you have a saddle, the only possibility of a saddle is to have one stable direction and one unstable direction. But in dimension 3, you may have, for instance, a saddle, say, with two contracting direction and one expanding direction, and another saddle with two expanding direction and one contracting direction. And then these invariant manifolds may intersect. For instance, assume that we're in dimension 3. You have that the one-dimensional manifold intersect. You know that you cannot have transversality because you have only 1 plus 1, that is 2. And the other manifolds may also intersect, and it is what people call algebra dimensionals. And then what Jacob made this conjecture, I guess, let me say, in the 90s. And well, this conjecture motivated many people, but then what we think is, well, the conjecture by Jacob say, well, you have hyperbolicity, and you want to understand what happens in the other side of hyperbolicity. And then what we prove, let me state the theorem. The theory is you consider the space of diffuse of class C1 plus alpha in a three-dimensional manifold. You assume that this diffuse is volume preserving. Okay? And then you have two possibilities. You have that either the system is an also, that is exactly correspond to the hyperbolic case here, or the system has some non-hyperbolic method, hyperbolic. Let me try to explain the second part of this theorem. Let me try to explain to you what is a non-hyperbolic ergodic method. Well, this is the class of system that we consider by the very nature of the problem. We are in a context that we call partial hyperbolic. Partial hyperbolicity. And let me use assuming what follows, well, everything that I am going to say. Well, some things are true in higher dimensions, but I don't want to bother you with higher dimensions. What means partial hyperbolicity in our setting is that you have that the tangent bundle of the manifold M is split in 3 directions, which are invariant directions. The first direction, we have a uniform contraction. In the third direction, we have uniform expansion, and we have another direction that is invariant in between, and well, we don't know what happened with this direction. We may have some contraction, we may have some expansion, but what we know, sorry, is that if we have contraction here, this is contraction, well, this contraction here is stronger than the contraction here, and if we have some expansion here, this expansion is stronger than the other. Okay, well, that means that if you are trying to find some non-hyperbolicity of the system, well, here you have a system, some strong contraction, some strong expansion, then all non-hyperbolicity comes from what happens in the central direction. And let me also observe that one that you have this sort of system with 3 invariant bundles, you may not have this kind of homogeneity tendencies. Okay? You only may have this kind of cycle, but it's not very relevant for my talk. And then, well, when you have a splitting like this, you have the oscillated theorem. That it is setting, well, we don't need all the strength of the oscillated theorem, but the oscillated theorem tell us the following. Well, if you take mu, that is an ergodic measure, that is that if you have a set that is invariant, they have either full measure or zero measure. You cannot split the system into invariant pieces with a positive measure. Then you have this measure, and then the oscillated theorem tells you that for mu almost every point, you take a vector in, well, non-zero vector, of course, in the central direction, and then you have that this limit is a number that is constant and independent of the point. And this is called the central Coulomb point. Okay, and now we say that the measure is hyperbolic. Is this number is non-zero and non hyperbolic is this number is equal to 0. Okay, well, let me tell you that of course that trying to find non-hyperbolic ergodic measures is a difficult problem, especially if you try to find measures with higher complexity. And my plan today is to first, well, let me say two things. First, when you have hyperbolicity of the system, then you can use a lot of techniques coming from testing theory and things like that. And then you can get many properties about the system. But when you have a zero Coulomb exponents, well, you are quite lost, and then it's very difficult to deal with this kind of message. Okay, what we say is, well, either we are in this case, or in the contrary, all the hyperbolicity is what I like to say that, let me summarize the way that I like to rephrase this theorem. The non-hyperbolicity is detected in the ergodic level. That means that you can construct a measure with some zero exponent. Let me also, well, we expect, well, we know, by the way, in the cases that we are, I have, well, no, sorry, here is the torus, sorry, oops. It's not any, we have some result in more general, but the result today are in the torus. I apologize by this mistake. And now I need to, sorry. Okay. Okay, yes. Well, you expect that the situation is more or less like this. This is a figure that like Jacob loved to do in his talks. You have here the hyperbolic region, and you have here the non-hyperbolic. And typically in this setting, both regions are big. These regions contains open sets, okay, are big regions. And then you know the Cook-Esmel theorem. You can state the Cook-Esmel theorem in the conservative case. The Cook-Esmel theorem tells you that the periodic points are generically hyperbolic. And then, well, you may have, of course, if you have some no hyperbolic periodic points, that means no hyperbolic periodic point. Well, then immediately you consider the measure, the ergodic measure supported in that orbit. And then you immediately obtain a measure that is not hyperbolic. Okay, but the number of diffeomorphisms, or the quantity of diffeomorphisms that you can do obtain this kind of non-hyperbolic measure is very small, because you have a set that is, well, the complement, you know, this is a non-generic property. And this means that most, I don't know, many, of the non-hyperbolic measures that we obtain here are measures which are not supported in a periodic point. Well, now let me just explain what is the plan of my talk after this introduction. Well, let me, before, 1 second, sorry. Okay. There is an informal conjecture. Indeed, I state the theorem is not correctly stated. I apologize by this, sorry. There is an informal conjecture. I don't know, perhaps 95 or some, or 2000, you say, due to Enrique Pujals. Well, Enrique, well, here I am dealing with dimension 3 diffuse, which are partially hyperbolic. And then the conjecture of Pujals say the following. There are 3 types of partially hyperbolic diffuse, like this. The first category is what is called derived from anosome. That is, you start with some conservative anosome and do some sudden node of free bifurcation, and then split the DA anosome. This is called the DA maps. A second possibility is time 1 of anosome vector fields. And the third category is the following, are called skew products, which are very important for us and for me. Is the following. Consider that you start here with your favorite anosome diffuse, for instance this one. This is a torus. Okay? It's a conservative mass, and then you multiply by some circle. You may have, for instance, the anosome times the identity. And then you may perturb this kind of diffuse. And what happens in this setting is that these circles are called normally hyperbolic circles. And the normally hyperbolic circles behaves more or less as the hyperbolic periodic points. If you have a periodic point and perturb the periodic point persists, and then you have this situation. That means that you have a foliation by invariance circles, and you do a perturbation of this kind of maps. And then, well, what you have is another system that also have a foliation by circles. But of course, the circles are not exactly circles anymore. But these are the third type of systems in the classification of Pujas. Pujas made this conjecture during a talk. I think that everybody give the credit to Enrique, but give the credit of a wrong conjecture to somebody that didn't make the conjecture is a little unfair, but it's okay. But I think that anyway, Enrique was very proud about the conjecture because many people think about the problem. When all these kind of systems fall in a category that is called dynamically coherent. Dynamically coherent means the following. Dynamically coherent means that here you have three foliations: the strong stable, the strong unstable, and the central. Well, you have a theory due to Hirsch in the 70s, I guess, or before perhaps. They prove that you always have a foliation that is called the strong stable foliation that is tangent to the strong stable foliation. You have another foliation that is called the strong unstable foliation that is tangent to the unstable bundle, but you don't know if this central foliation integrates to another invariant foliation. When you have that this central bundle integrates to foliation, then you say that the system is dynamically coherent. And during many times, the people working on partial hyperbolic theory thought, well, all partial hyperbolic systems are dynamically coherent, but it is not true due to a series of written works by Bonatti. My God, I cannot forget my Gogolev, Potri, and I am forgetting a name. My God. Let me see, I have a name here. Oh, let me know this, as this conference is recorded, Bonatita. I don't know, because they have many people with different combinations and they don't want to Google it. But I think that Hammerlinder, you know the names that you need to put here. I don't know if Torber is also Hammerlinder. And also Bertaume, or many people. And this is now a very active line of research. Well, what we prove is that for these three types of systems, we prove the conjecture, the dichotomy that I started. Either you have a hyperbolic system, or you have a non-hyperbolic method. Pay attention that here we don't have any perturbation. We don't have any generic property. You have either the system hyperbolic or you have a non-hyperbolic method. And now let me try to tell you some words about non-hyperbolic methods. Okay. When I talk about hyperbolic and non-hyperbolic method, I am always assuming that the method is ergodic. Okay? I don't want to take a silly combination of hyperbolic method to get some exponent equal to 0, okay? Well, no hyperbolic measures. Well, there is a paper by Anton Gorudetsky well, Yuri Lyasenko, Klepsy, and Nausky of these 4 people, where they introduce a method for 2 things. Well, the setting that they consider is a setting that is today is called step SQ products. That I will explain in 2 minutes. Well, they started in the setting of the step SQ product, and they consider 2 problems. The first problem is the following: when the limit of ergodic measures is ergodic. The ergodic measures have the property that when you take limits, they don't accumulate typically on ergodic measure. And the second problem is how to get 0 exponents. Let me now try to explain the setting of this for people. You consider here, say, the shift of 2 symbols, that is 0, 1. And here you consider the shift, that is you just move sequence to the left or to the right according to your preference, okay? And multiply by the symptom. Okay? And then what they did is the following. Now in the circle you consider 2 maps. One map that is simply north-south Morse-Mail map. Very annoying, nothing very well. You go from the south to the north. And the other map, let's take some irrational rotation. Just to simplicity, we don't need to take an irrational rotation. And then, well, you consider this system from this space into itself, where this method is extended in many directions to the diffeomorphisms, many situations that I don't want to discuss. But the idea that they have is, you look to this system, what happened with this system? You start with a point here, and essentially what you need to do is to select the itineraries. You take a point, and then you take the sequence, then you can decide the sequence that you want to apply. And then, for instance, I decide, well, to apply this map, and then I put a row of zeros. At some moment, I am very close to the north, and when we are very close to the north, we start to have contraction. And then we stay in the north the time that we want. And then when you are trying to stay in the north, you decide, well, I have here an irrational rotation. And then when you have an irrational rotation, you can travel along the circle. An irrational rotation is a minimal transformation in the circle. And then you start to walk with this irrational rotation. I am presenting you the super simplified idea of the proof. And then, well, you can decide to land very close to the south. And during this period, this moment, you do nothing because you have an isometry. Then you are very close, and then you start to have expansion. And essentially, if you decide to stay very close to the south, you can concatenate a huge number of expansions. Then you can concatenate the huge number of expansions, and then you, well, decide go to the north, have the contraction. In other way, what you can do is that you can concatenate expansion and contraction more or less as you like. Well, perhaps some of you can, let me use, if this figure tells you something, it's okay. If it tells you nothing, don't worry. This is the famous Bowen eye, where you have no average. Well, it's not the same, but has the same flame. I stop here my small parenthesis. Well, and then what these people do is when you have this kind of configuration, they prove the following. Well, you start with some periodic orbit, say a contracting orbit, contracting for instance, and then this is the first P1, the first test. And then what you need to prove is that under that condition you can now construct another measure that do the following. It mimics the first measure for a very long period. Well, I am tired. And then at some moment, the measure jump has a small bulk outside. And then, well, you have a measure of a very big period. So that, well, you have a part of the measure that mimics what happened the previous measure, and then you have a walk outside. Well, if you want to get something that is ergodic at the end of the day, you need to estimate what is the proportion of points here than the proportion of points there. If you are not you don't take care, with my, well, now let me explain. The second orbit, well, you have the same thing. You are mimicking the second orbit for a long period, and then you jump to another part. And then you repeat and repeat and repeat. And then what they prove is that if you do the average correctly, and you consider the measures UN supported on Pn, on the orbit of Pn, then this measure compared to some measure that is ergodic. Nowadays, we call this type of measure, which are obtained in this way, as a limit of periodic measure, with this shadowing and tailing. You call this tail, shadows. When you obtain a measure that, using this method of tailing and shadowing, you call this measure GIKN. My God. And well, there is just another footnote. There is a result by Dominique Degner. I think that is like this. Vodka. Well, I don't know Polish characters. That they prove that this measure has 0 entropy. That is a measure with low complexity, but I don't want to talk about it. Well, and then you have a method to produce ergodic measure, but this doesn't tell you anything about the hyperbolicity. But if you have now look carefully what we are doing, well, we can select this first orbit is contracted. Well, let me repeat the figure. You may have the first orbit that is contracted. And then the new orbit, the time that is nearby this contracting orbit, you have contraction because you are close to a contracting orbit. Well, you have contraction. And then when you use this tail, is to visit and expanding region. Now I want to discuss, I think that I have still 15 minutes, no? I stayed a little late. No, but I started late. How much time I have? 10 minutes, okay. You know, I am complaining because I am staying later, but it's okay. I promise to finish on time. What we need to think? Yes. Well, a difficult problem in general in dynamics is that you have two regions. Say a region that is contracting and a region that is expanding. Let me say contracting and also attracting. When you are in an attracting region, by the very definition of attracting region, if you have a point here and are in an attracting region, you go inside. And then concatenating contracting iteration is very easy. It's given by the nature of the dynamics. You have an attractor, everybody goes inside. But if you have a point in an expanding region, what happens is when you are expanding, and typically points escape. And then the difficult point always is how to concatenate expanding iterates. Well, this is in general a very difficult situation. To concatenate expanding iterates, you need to go to dimension 3 at least. Then let me try to explain this in this skew product. This is the circle. In the circle, we have two maps, the map F0 and the map F1. Then assume that the map F0 expands in this region. In this region, you have expanding derivative bigger than 1. You may have this. That means that in the other side you are contracting, okay? But you may have a region where you have expanding. This is the expanding region for the map F0. Of course, I am here. Now it's not coherent with the rationality of the rotation. Let me take a little my mind. But you may have, well, that in the other region, you may have here this region is the expanding region for F1. And then you take a point in the circle. Then, once you have this configuration, it's very easy. You always have the possibility to concatenate to expansion because, well, the point is here. Well, it's here. Then I can apply if not that is expanding. No problem. Consider the iteration. Go here. Well, now the point is here. And then you can use the other map to get an expanding concatenation. Of course, this is a very easy situation, a very easy, simple model, how to explain how to concatenate expansion. Well, you can try to do these kind of things in a more efficient way. That is what I introduced with Cristian Moratti in the 80s, something that we call blenders, that let me to explain a 2D version. You can do this 3D, but I don't want to bother you too much. Assume that you have a rectangle. Think that you have something similar to a horseshoe. And then you assume that you here has if you want to like to think in dimension 3, you may have another contracting direction. But forget this contracting direction. And then, let me erase. You may have this disk, where this disk goes to the whole square. This is an endo in dimension 2. but if you put this endo in dimension 3, it's not anymore an endo. And then you have another rectangle that is mapped into the whole square. If you like one-dimensional dynamics, the figure is this, the one-dimensional model, something like this. If perhaps for some of you, this tells something, Bernoulli convolutions. If this doesn't tell you nothing, don't worry, it's Bernoulli convolution. Then that means that here, you always take a point, you can concatenate iteration all the time. Here, how do you do this? You take this like this. You have this like this. Then the image of this, well, in this part you have expansion. And the image of this is something like this, for instance. And then here you have this region where you have expansion. But you need to do this in dimension 3, but this is the idea. So then you have the idea how to produce concatenation of expansion. But this is a very specific mode. Although you have this kind of blenders very frequent in many settings, we cannot use these techniques to deal to get expansion. And then with this, for me, from the technical point of view, that is perhaps for me the most.
There is no relationship between the coefficient of expansion.
Here, no, this is, blenders are very simple, hyper simple situation. It's not sophisticated at all. It's just you only need to have expansion. If you want to deal with Bernoulli convolution, I have some answer that is absolutely continuous, blah, 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 blah. This is another topic, and then you are completely right that if you think in Bernoulli convolution, you need to take care about the slopes, blah, blah, blah. But here we are in a very, very hyper simplified model. We don't care about this kind of things. Okay? Well, I have 5 minutes, then I need to tell you something coherent. Then, well, for me, a very interesting new ingredient that we bring to this field is that we call multiply expanding diffuse, let me say. Okay? And then the moduli expanding diffuse, so you can say, diffuse, you can say about the moduli expanding property. You don't like to use diffuse. Is the property that will provide us, well, is here, no? The word expanding. When you have a system that is mostly expanding, we will have a very efficient tool to recover expansion or to concatenate expansion. This is below to concatenate expansion. Then I will explain what is a multi-expanding diffuse. I will state a new theorem and I will finish. 5 minutes. Okay? Well, this you have, multi-expanding diffuse is a very fancy ingredient for people working with partial hyperbolic dynamics. This appears in many settings. There are several definitions for multi-expanding diffuse. Different authors use different definitions. This is a little inconvenient, but let me explain what is our definition. Well, you have something that we call Gibbs, the people call Gibbs-U state. And before some of you ask the question that everybody asks, Gibbs-U state satisfy the Gibbs property? No. I don't know why Gibbs-U states are called Gibbs-U state, but the people decide to call Gibbs-U state, okay? You say that measure is a Gibbs-U state. Let me recall that we are in this partial hyperbolic situation. that we have three bundles with two tangent foliation, and then you have, when you have this measure and this foliation, you have that this foliation, you have the conditional measures. Okay, you have the conditional measure, and then you say that the system is your state if these conditional measures are absolutely continuous with respect to the vector. Okay, and you say that, well, this is a GPU state. The definition of a mostly expanding now is that, well, a diffuse is mostly expanding. Of course, a partially hyperbolic diffuse, blah, 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 is mostly expanding. If this Lyapunov exponent is positive for every mu gives US. Well, there is a result. I have no time. I plan to finish now, almost. There is a result by Diagan that say that when you have this kind of system, you know that the measure is every measure has positive exponent, but you don't know if this measure has uniform positive exponent. But the thing is that the Gibbs U states have positive, uniform positive central Lyapunov exponent. This will provide us the expansion. Okay, and now let me finish with the theorem that we use to prove the other results. I need 2 seconds, sorry. Okay. We have this theorem. That this theorem now holds in general. You don't have any restriction on the topology of T3. Well, that is the first step of all the construction. You have, of course, we are a set that is invariant. Of course, it's compact. Okay. And then you have that this set has two probabilities, two properties. Sorry, is U minimal. Okay. If U is every leaf of a point in lambda is contained in lambda and is dense. In other words, you have that this set is saturated by strong and stable leaves, and every leaf is dense. You can think that this is a very restrictive property, but if you have this kind of phenomenon very frequently in the real partial hyperbolic life, it is life exists. And you also have the mostly expanding property. You say that F is mostly expanding. And then, when you have this possibility, you have two possibilities, two things. Either lambda is hyperbolic, or it supports a non-hyperbolic. This is the first step of the construction. I have no time to consider, to tell you more things. Of course, now you can tell me, well, this has nothing to do with T3, it has nothing to do with DA, it has nothing to do with the skew product. Well, now we need to use that the diffuse in T3, the conservative diffuse in T3. Recently, there are a very, very rich theory about them. You have results about accessibility, many things, and then more or less what we do is, well, we need, in each case, the proof for DA is different than the proof for vector fields, time one vector fields is different to the case of a skew product. In each case, we do, well, use the recent results to the theory to follow in this case and then derive the theorem. But as I have no time and everybody wants to go to have a barbecue, thank you very much. I stop here.
Questions and comments?
No hyperbolic methods. You have a dichotomy, you have that either lambda hyperbolic set, or you have a non-hyperbolic method supported on lambda. Of course, you know, we want to prove the theorem. At the end of the day, at some moment, we will need to prove that this set is the whole manifold, and you have an also, but this is another, you know, you need to use different ingredients. For me, today, the goal of my talk is to try to call the attention of these gives you a state, which are very useful, and to explain, well, the same thing. But I have no time to... No, you have two possibilities, or you have that, or your system is here, or you have here some method that we will construct that is ergodic and not hyperbolic. That is the dichotomy, the beginning. It's a kind of, it's a dichotomy, either hyperbolicity or not hyperbolic method.
Hello. Can you perform something like the Gorodetsky-Ilyashenko construction if the base of the skew product is a unilateral shift?
I think so. This is a discussion that I always have with my co-authors because I am very poor on symbolic dynamics. All the construction that we do is looking forward, and in principle, well, you can do the same thing. Indeed, it's easier to do in the one-sided case. This is the same thing. I think that indeed. I think that yes, you do the same. You don't. I think that you don't need to change a simple word in the result, because you have approximation by periodic method is exactly the same construction. You only iterate forward in the construction by Gorodetsky and co.
Thank you, Lorenzo, for the nice talk. Good step in the direction of the conjecture, the original conjecture. Just a question. When you said F1 is irrational rotation.
You don't need to have an irrational rotation.
That's my question.
You don't need. You the only thing.
It doesn't matter, right?
No. Okay. The key that you need.
There will be no periodic point will appear.
No. Well, I think that you may have periodic points. I think that the key point here is that you, well, sorry, I need to be a little technical. You have these two maps, okay? And then you have the iterated function system associated to this map. By the way, under education, because I iterated system function only look to what happened forward, okay? And the property that you need is that every point, sorry, has a dense orbit. And now look that an orbit, you start with a point, then this point you can iterate by F0 and by F1, and then you iterate again, and then you have a tree, and what I am asking is to have this tree dense in the whole manifold. And then one of the magic things in the, in the Ilyashenko, the Gorodetsky and co paper, is that, you know, if you think about minimality is, when you think about the property of minimality, that is the property that every point is dense, you think, come on, this cannot be an open property. But what they say is, well, in this case, what they have is an open, in the appropriate topology, system of iterated function system with this property of minimality is dense. But I know that I was a little, I lay a little because in one side you have a rotation, but you need to, in any dough you need to have a secret ingredient.
Thank you. That's the question.
More short question, Regis.
As I understand, you're supposed to use a Jikin construction for the SKU product. So you are saying that always for the SKU product?
No, not for the SKU product. I am trying to tell you this, the proof. If you look to the SKU product, the magical point of the construction in the SKU product is that you have a contracting region. That these days, when I start to explain this thing, you have a contracting region. It's here, an expanding region. Okay, this is contracting, and this is an expanding. And then the property that we need is that we can go from contracting to expanding, and from expanding to contracting in finite time. And how do you go from contracting region to the expanding region? Using the minimal foliation. The minimal foliation provides you the transition, of course not for every point, but for many points. And then you go from one contracting region to the expanding region about the strong foliation. Then you can concatenate contraction, because to concatenate contraction you have some kind of trapping region. You can repeat, and to concatenate expansion you use the most expanding property. And then what we do is the first part of the paper, probably the referees can complain, well, you waste 5 pages repeating the construction by Gorodelsky and Co. Yes, we repeat the construction because we need to repeating it's the same thing, but it's different. It's something that is deeply inspired by the proof. The proof is the same, but it's different. See, that's
So,
the feeling of the...
We haven't time for more questions. So let's thank the speaker again. We have some messages.
Okay.